بسم الله الرحمن الرحيم. أيحسب الإنسان أن يترك سدى ألم يك نطفة من مني يمنى ثم كان علقة فخلق فسوى فجعل منه الزوجين الذكر والأنثى أليس ذلك بقادر على أن يحيي الموتى. صدق الله.
Aims to bring together many experts and researchers from various institutions and universities who are interested in this field. Currently, the Faculty of Science consists of two departments, Department of Biotechnology and Genetic Engineering and the Department of Mathematics and Basic Sciences. The department currently encompasses 3 full professors, 2 associate professors, and 4 assistant professors with 2 master degree lecturers. Through the years, the number of graduates reached up to 500 students, and it is currently hosting 200 students distributed over 4 levels. Now, actually, we're going to start the talks, and the first talk is going to be hosted by Dr. Mu'taz Sheikh Salim. Dr. Mu'taz Sheikh Salim got his PhD in pharmaceutical technology from the University in Manchester in 1981. Over the course of his professional career, he had different posts in leading positions like head of department, dean of faculty of pharmacy and faculty of science, vice president of Royal Medical University, Philadelphia University, and currently he's the president of Philadelphia University starting September 2015. Since then, he had led an intensive, noticeable infrastructure renewal and refurbishment, as well as programmatic enhancements across all departments. Because of his medical background, he has been and still is dedicated to enforce a stronger scientific platform for faculty members, research scholars, and students in pharmaceutics and in human diseases and disorders. Dear guests, please join me in welcoming Dr. Mu'taz Sheikh Salim.
Bismillah, honorable guests and partners, dear participants and colleagues, ladies and gentlemen. On my own behalf and on behalf of Philadelphia University, represented by the Department of Biotechnology and Genetic Engineering at the Faculty of Science, it gives me great pleasure to welcome our partners from the University of Tübingen, as well as all participants and speakers from the University, the Royal Medical Services, the University of Jordan University Hospital, and Al-Isra Hospital, to this important symposium, which is entitled the First German-Jordanian Meeting, Molecular Genetics of Human Diseases. This event represents the first meeting for the German-Jordanian partners in the project Genetic Causes of Autosomal Recessive Intellectual Disability, which is funded by the German Academic Exchange Service. It aims to present the result obtained throughout the first year of the project and to shed light on recent developments in genetics of intellectual disability. In addition, it aims to foster the dialogue and create bridges between.
Dr. Olaf has more than 20 years of experience in genetically caused disorders. His main focus is on the neurodegenerative diseases, both from clinical as well as from basic research perspective. Especially, he's focusing on the Parkinson, dystonia, and spinocerebellar ataxias. He has been a coordinator of numerous international, European, and national funded consortia. He published more than 250 papers. He is known for the generation and characterization of numerous animal models of these diseases, in particular of transgenic rat model. Dear guests, join me in welcoming Dr. Olaf. Olaf, please.
really great pleasure to be here. It's, as you may imagine, my first time to be in Jordan, and it's always fantastic to meet so many enthusiastic scientists, so many very friendly people who welcome us very much, and we really feel it a bit like home. So you may ask, what is home? And of course, home is not only the country, home is where the friends are. And as I took the textbook and the travel guides to see how Jordan looks like, you may wonder what is home to me and where we come from. So my hometown right now is Tübingen. It's a very small town, much smaller here than Amman. We have about 100,000 people living there. We are definitely a university city, so we have more than 30,000 students. So you may imagine 1/3 of the entire city is very vivid life and young people enthusiastically studying in different courses. So that is how Tübingen looks like. So it's a wonderful small city. However, Tübingen is known for me, in particular as a human geneticist, that the DNA was discovered here. So Friedrich Miescher discovered the DNA in this castle, which still exists. And this is the kitchen where he prepared the DNA for the first time. And I can assure you the labs look a little bit more sophisticated right now. So Tübingen is also known, however, that Aris Alzheimer first published this case on Auguste Lie. So the city is strongly associated with Alzheimer's disease. He announced this case on the pathology of Auguste in this hospital of psychiatry, and you see the very close distance to our hospital. We are here on top and in this building and this floor. So this is the major part of human genetics where we are hosted right now. Tübingen these days is known in Germany for establishing the first German rare disease center as well. So we at one point realized that we have so many million patients affected with rare diseases, and we estimate about 3 to 4 million alone in Germany. However, we do not really have a certain healthcare structure for these patients. What is difficult for them to find an entry into the healthcare system. So they are going to a general practitioner, they don't realize that they have a rare disease. So we started out to give them a structure with a patient portal where the patients or the doctors may call, coordination between these centers, a registry, biobanking, publicly available. So we teach the doctors and so on. We do fundraising with a primary goal to establish clinical studies for these patients. You may know that we have about 7,000 to 8,000 rare diseases, but we only have about 70 drugs worldwide with an orphan disease status. So it's a long way to establish a structure for them and to develop drugs and treatment for the different patients who definitely deserve our attention. Within of these rare disease center, we have one subspecialty, what is the rare neurological and developmental diseases, which is really working as a very good extension for all the other subspecialties. And within of these rare disease center, within the rare neurological and developmental disease center, we do meet once a month 50 medical doctors from different specialties, from pediatrics, from genetics, from neurology, from radiology, and so on, to discuss patients, what they may have and what disease may underlie their condition. And in this particular subspecialty, we are very proud and very happy to have now a good going, long-standing collaboration with Jordan here. And a particular topic of, is he right now? Over there. He made this project really give it a life, and it wouldn't work without him. So Tafek, thank you so much. I really deserve it. Without Tafek, we wouldn't be here because the project wouldn't be running. Without Tafek, we wouldn't have a joint project funded by the DAD, and I'm particularly thankful that you are here today and watching the progress what we have reached. And without Tafek and all the people here with we wouldn't have this wonderful meeting. So thanks again for that. Now, give you a little bit of an overview where we believe human genetics or medical genetics may guide these days many specializations, many directions, and maybe the future of human medicine. And why we think so is because we have new technologies in place which change the entire system what we are used to. The used to be was what we call traditional genetic diagnosis. So usually we did see a patient, usually we did meet the parents of this patient, we counseled and discussed what condition they underlie, and then usually we have maybe one or two genetic tests and say, well, this could be the condition of the patient. And that is where human genetics stops in the old days. We had not an integrated plan to develop drugs for these patients. We had not an integrated plan how the general care of these patients in the healthcare system would take place. Who is responsible, at what frequency these patients should be seen, what specialties should see these patients, and so on. We have to integrate these patients into, in particular, the university life right now. This is possible now because we have these new technologies, what is called next generation sequencing. And these new technologies, although expensive, are very cheap compared to old traditional ones. So one of these equipment here, one of these traditional sequencers costs about 300,000 euro. But you can imagine that when you need 100,000, or the new techniques is basically replacing 100,000 of these genes, and one of these sequencers costs about 800,000. So it's a huge progress what we made based on the Human Genome Project. Why is this so important? Because we can now basically within a couple of days sequence entire genomes of the patient. Although we still have problems interpreting the data that we have, at least for most of the problem. However, in genetic conditions, we do make a lot of progress now using this technology. What can we do with this technology? First, we can run and diagnose a lot of what we call genes in parallel, and looking for genetic heterogeneity, seeing the broad range of the clinical phenotypes, and learn a lot what genetic conditions may do to the patients. These panels, how we call them, they may have may reach between 1 and 1,200 genes in parallel. So very efficient, very quickly, and we are even able to run what we call the Mendelians, that is basically all the genes which are known to be associated with a genetic disease, and they count to roughly 5,000 genes right now. What we can do is we have this high coverage, high diagnostic value and sensitivity. We find mutations in many genes, not in all of them. The disadvantage of these panels is that we have to design them, we have to implement them. It takes about 3 months, 6 months, or even longer. And so during this time, a lot of new genes are being discovered, and we have to integrate these new genes again into the panels. This is quite some effort, even for our lab. But you see for the certain conditions what we have, ataxia panels, more than 140 genes, for paraplegias, more than 110 genes, just for intellectual disability, more than 1,000 genes, and it goes on and on the list. And of course, we are very efficient then in the way to helping the patients in finding the right diagnosis. However, as I mentioned, we have to always be adapted to the new system. So we are switching to whole exome or even the genome analysis. And this is what we are doing in the project with the DAD together. This is what we are applying to your patients here from Germany. We should not imagine whatsoever that using all the exomes, that means all the informative material of our genome, that we solve everything. Here I show you a paper from Jacob et al. In 2013. What I didn't really like when it was published, but thinking and going over the paper more and more, I think it's even worth to show it here in the audience, because they didn't really sequence a lot of patients. They just published 5 patients. And in these 5 patients, you can see all the ones in red, although having found a lot of pathogenic mutations, they are not really sure about the diagnosis of the disease. So that is true because we don't know a lot of these pathogenic mutations. Sometimes we don't have any information on the genes where these pathogenic mutations have been found. And sometimes patients have a phenotype which we cannot associate it currently with the patient. So also this applies to the patients in Jordan. We will not solve all the cases, and we will have unsolved cases what we have to follow up for the upcoming years. Now, the other problem is looking at the databases, and this is, I have to admit to a scientist, basically a shame. 1/3 of all the data are not correlated. That means you go into the database, think you have solved the case, you find the mutation. However, several of these, and 1/3, that is really a huge dimension, is not really well annotated, so we may run into diagnostic problems. Also, as I mentioned, of these pathogenic mutations, about 8% of the population, so that's basically us, also have pathogenic mutations with stop codons and on both alleles, and we are functioning perfectly normal. So we have to find out what is pathogenicity and what mutation really causes diseases. The other thing is that we discover using, so that's an advantage now, that we assign these patients sometimes a totally new diagnosis when we use the whole exome, and they were running for the last couple of years under a wrong diagnosis. And I give you one example for this, part